Hello class, this is Rivero Fonseca. Today I will be talking about the chemical kinetics. So if chemistry is the study of change, then chemical kinetics is at its core it's pure chemistry. It's the study of how fast, how quickly reactions take place. So section 1. It's going to be about the solvolysis of terbutyl chloride in water. Solvolysis of terbutyl chloride in water is the conversion of terbutyl chloride to terbutyl alcohol, terbutanol, right? Where water acts as reactant as well as solvent. In the lab, I'm actually conducting a reaction like this almost every day, where pyridine acts as a base and also solvent. So there are several kinds of these kinds of reactions that you can talk about, that you can describe using such terms. There are solvolysis, where the solvent is the reactant, hydrolysis, when water acts as reactant, and alcoholysis, where alcohol acts as a reactant. Note the difference between reactant and reagent. That might be in the quiz. If you want to know, you could just Google or you could email me. I prefer you to email me. So here you can see the reaction. Terbutyl chloride, and you have water, and you have terbutanol and hydrogen chloride. You could call this a substitution, right? So this is the possible mechanism for the reaction. You have terbutyl chloride, and the electrons choose to stay with chlorine. And once the chlorine becomes the chloride ion, you form a carbocation. So this is the rate determining step. This leaving group, although it's a good one, it still takes quite a bit of time. And afterwards, a fast step is water attacking the carbocation. And you can think about this mechanism as pretty much the opposite of what you did last week. But once you have this also occurs very quickly, and it's the actual substitution. The chloride ion steals this extra proton that the oxygen doesn't want, and the electrons stay here with the oxygen, therefore balancing the equation with charge. So this reaction is a nucleophilic substitution reaction. Water is the nucleophile. In this particular reaction, the first step is slow, and the next steps are fast. But this is the key part. As the rate determining step contains only one reactant, terbutyl chloride, the reaction is unimolecular. Thus, this is nucleophilic substitution, SN1. Again, here's the mechanism. So the rate of this SN1 reaction, it depends on the concentration of terbutyl chloride, since this is the rate determining step. The concentration of the nucleophile, the water, has no effect on the reaction. Usually we add an excess of that. So here you can see the formula. The rate of the reaction equals K, an experimentally determined constant, times the concentration of terbutyl chloride. Right, it's a first order reaction. So this will be the demonstration for the derivation of the rate equation. So we know this is a law, right? So the rate is equal to the constant times to a constant times the concentration of the substrate of terbutyl chloride at a given t. Here you can see the t. The rate of loss is therefore this, is the derivative of the concentration of terbutyl chloride with respect to time, but negative because that rate is negative because you're going to lose terbutyl chloride as time passes. So that rate, which is negative, is going to be equal to that constant, that experimentally determined constant, times the concentration of terbutyl chloride at any given moment. Now we arbitrarily choose t equals 0, and we call that concentration at t0 C naught. So after integrating, we can integrate this, right? We move the dt to the other side and we integrate. We end up with this, with the natural log of this ratio equals k times t. And we can rearrange, we can convert to log, and we can have a neater formula. So again, this is the reaction, SN1, and we look at the ratio. 1 molecule of terbium chloride creates 1 molecule of hydrogen chloride. So then we'll use these facts to determine, to further substitute into the previous formula. At the end of the reaction, when T approaches infinity, all terbutyl chloride, well, all the chloride from terbutyl chloride will convert to HCl. So the concentration of HCl at infinity equals the concentration of terbutyl chloride in the beginning. Now at any time, HCl at any moment equals that initial concentration of terbutyl chloride minus the concentration of terbutyl chloride at any given moment. So then we rearrange and we insert that into the previous equation. Now you'll use that equation as you figure out the values experimentally. The value of HCl at time t is determined by withdrawing an accurately measured sample from the reaction, referred as an alkyl or sample, and then quenching the alkyl with acetone and titrating with a base. It is not necessary to use a standardized solution of base for the titrations. We do use a standardized solution in my lab. Usually labs will have that. Sometimes it's 10% for an acid, 15% for a base. As long as the same base solution is used for all titrations and the volume of all alkyls are identical. Additionally, it is not necessary to calculate HCl at any given moment or HCl infinity, because the value is directly proportional to the volume of the base solution required to titrate the alkyl. Again, this you will find out experimentally, and we use NaOH as that base. Whatever amount you use of NaOH, that's the same amount that you use, or that of HCl that was consumed, which will tell you about the terbutyl chloride that was consumed, right? You're basically going to be measuring at time t how much terbutyl chloride is being consumed. So now the procedure. You prepare your burette with 0.04 molar NaOH solution. You fill your 50 ml burette with 0.04 molar sodium hydroxide solution. You prepare your stock solution. So you use a plastic pipette. You measure 1.2 milliliters of terbutyl chloride in a 100 ml volumetric flask. So again, you know how much you're putting in, and as time changes, as time goes by, a set amount of terbutyl chloride will be consumed. And then you fill your 100 ml volumetric flask with 1:1 water and 2 propanol solution. This will be where you will draw your alkyls and conduct your reaction. So after you add and combine them, the stopwatch, you should start measuring time then. You also must prepare your infinity solution after you conduct the titrations after this amount of time. So using your 10 ml pipette, you take 10 ml stock solution in 125 milliliter Erlenmeyer Meyer flask. You add 10 milliliters of water and you mix well. And keep it aside. Again, you'll use it afterwards, after your titration of the stock solution. So at 10 minutes, using a 10 milliliter pipette, you take 10 milliliter stock solution into a 125 milliliter Erlenmeyer flask. You'll do this at each interval. Then you add 10 milliliters of acetone to quench the reaction, and you add 1 to 2 drops of bromothymol blue solution, which will tell you when the reaction is done for that alkyl, and you titrate with 0.04 molar sodium hydroxide solution till the end point. You'll see the color change. And you record the sodium hydroxide solution you needed for that titration. So again, you're taking these molecules at different intervals of time, and then you quench and you titrate. Next up, you titrate your infinity solution to get that value. Remember, from your formula, you need that value that you calculate from the volume of sodium hydroxide. To that infinity solution, before you do anything to it, you add bromothymol blue, 1 or 2 drops. And now your infinity solution, since it's acidic, it should have a yellow color, and then you titrate it until it approaches a color change. You titrate it, and you record the volume of sodium hydroxide you need it. So you should come up with a table like this, right? And these are the approximate values that you would have used. You plot your graph, and that's it. I hope you learned something new today. Please ask me, email me any questions. My email still works, as yours should too. Thank you very much.